All right, today we're talking about quicksort. Now that might sound a little technical, but trust me, this algorithm is working behind the scenes in your life way more than you think. It's one of those invisible engines that makes our digital world, well, work. So today, we're going to pull back the curtain and see exactly what makes it tick.
Okay, so let's just jump right in with a quick question. Think about your social media feed, right? Or the leaderboard in your favorite game, or even just the results you get from a Google search. What do all those things have in common? I mean, on the surface, they seem totally different, but they all share this one fundamental secret.
And the answer? It's all about one single, really brilliant piece of code called quicksort. You can think of it as the ultimate workhorse. It takes huge, messy piles of information and just sorts it all out, neatly and, most importantly, super fast.
So, how widespread are we talking here? Well, this isn't some niche thing for computer scientists. No way. This algorithm is basically everywhere. It's part of the DNA of the software we use every single day. I mean, really think about it for a second. When you're on Amazon and you sort products from low to high price, that's probably quicksort. Or when you're scrolling through your photo gallery and it's all nicely organized by date, yep. Even just sorting the contacts on your phone alphabetically, quicksort or something very much like it is that invisible hand that's taming all that digital chaos for you.
Okay, so what is the secret sauce here? What makes this thing so effective, so popular? Well, the real beauty of quicksort is that its core strategy is, honestly, brilliantly simple, yet incredibly powerful. At its core, it all comes down to a classic strategy called divide and conquer. It's a simple idea, really. Instead of trying to tackle one massive, overwhelming problem all at once, like sorting a million items, it's much smarter to just break that huge problem down into smaller, bite-sized pieces that are way easier to solve. And it does this using 3 basic steps. First, you pick a pivot. You just grab one element from the list to be your sort of anchor point. Then, step 2, you partition. This is the key part. You shuffle the list around so that everything smaller than your pivot ends up on its left and everything bigger ends up on its right. And finally, step 3, you recurse. That's a fancy word for just do it again. You take those 2 smaller lists you just created and you repeat the whole process, over and over, until everything's sorted.
Okay, I know that might sound a little abstract, so let's just walk through a really simple example. Honestly, seeing it in action is when it all starts to click. So here's our messy, unsorted list of numbers. Now we need to pick a pivot. You could technically pick any number, but a common way to do it is to just grab the last one. So for us, our pivot is going to be the number 4.
All right, now the magic happens. We start the partition step. The algorithm basically just marches through the list and compares everything to our pivot, 4. And as you can see, every number that's smaller than 4 is getting shuffled over to the left side. And boom, partition complete. Now look at this. This is the really cool part. Our pivot, the number 4, has magically landed in its final sorted position. See that? Everything to its left is smaller, and everything to its right is bigger. The whole list isn't sorted yet, not even close, but that one number is exactly where it's supposed to be.
So, what now? Well, we just do it again. We've divided our big problem into 2 smaller problems. We have that little list on the left, 2, 1, 3, and the bigger one on the right, 8, 5, 7, 6. The algorithm just applies the exact same logic, pick a pivot, partition, to each of those smaller lists, and it keeps doing that until there's nothing left to sort.
Okay, so it seems pretty amazing, right? But, like any powerful tool, quicksort isn't perfect. It's not a silver bullet. There are some really important trade-offs, some pitfalls that you have to know about.
And the biggest trade-off is all about performance. So have a look at this table. In the best case, and more importantly, the average case, which is what you'll see almost all the time with random data, this thing is blazingly fast. We call that O of n log n time. But, and this is a big but, there's a worst case scenario. It's rare, but when it happens, the performance just tanks. It drops to what we call O of n squared, which is, well, it's a lot slower.
So when does this disaster scenario actually happen? It's all about making a bad pivot choice over and over again. Imagine if you're sorting a list that's already sorted, and you always pick the biggest item as your pivot. Instead of smartly dividing the problem in half, all you're doing is lopping off one element at a time. It's just horribly inefficient. The whole divide and conquer strategy completely falls apart.
This naturally leads to a comparison with its main rival, another algorithm called merge sort. You can think of it like this. Quicksort is the rocket ship. In most cases, it's just faster and uses less memory. It's built for speed. Merge sort, on the other hand, is like a tank. It's not always the fastest, but it gives you an ironclad guarantee that it will never hit that terrible worst-case performance. So it's a classic engineering trade-off. Do you want blistering practical speed, or do you want absolute certainty?
So that begs the question, right? If there's this risk, this potential for a catastrophic slowdown, why is quicksort still one of the most dominant, most widely used sorting algorithms on the planet?
Well, the answer really comes down to three key things. First, as we've said, its average speed is just fantastic. Second, it's incredibly memory efficient. Because it sorts in place, it doesn't need a bunch of extra memory to work, which is a huge deal. And third, it's cache-friendly, which is just a nerdy way of saying the way it works plays really, really nicely with modern computer hardware, giving it yet another speed boost in the real world.
And that amazing combination of features makes it the top choice for some of the most critical systems out there. We're talking databases sorting through billions of records, operating systems juggling all the tasks your computer is running, even financial systems processing huge volumes of transactions. For these systems, that real-world practical efficiency is just more important than the tiny theoretical risk.
So that kind of leaves us with a bigger thought, doesn't it? The incredible success of quicksort is really all about a trade-off, choosing incredible speed for the average day over a tiny risk of a really bad day. What does that tell us about the world we're building with code? It tells us we often favor what's practical over what's perfect. It's a bet on being fast and efficient 99.9% of the time, and that bet is what has shaped the incredibly powerful digital world we all live in.